So let's take a quick review of all the tests we have to decide whether or not a series converges. We've got the p-test, so that is if your index, if you have something of the form 1 over n to the p, if p is greater than 1, then your series converges. You have the integral test, geometric series test. That ratio that's part of your geometric series has to be less than 1 in absolute value. Telescoping series is also a means to decide if something converges or diverges. And then there's one other one. It's the nth term test. And this one you got to be careful with because the nth term test only does so much. You remember what it does? What can the nth term test do for us? It can prove divergence. It can't show convergence. Cannot. But it can show divergence. So can only show convergence or divergence. Only show divergence. It can't be used to prove convergence. So let's see. So that gives us 1, 2, 3, 4, 5. 5 tests. 5 tests simply isn't enough. You need a couple more. So let's do a couple more here. In this section, we're going to do the direct comparison test and the limit comparison test. So we'll start with the direct comparison test. And the direct comparison test is for positive valued terms. So it's for series whose terms are all greater than or equal to 0. Actually, just greater than 0. So 0 is less than a sub n is less than b sub n. Let me just check. This actually could be a less than or equal to. Now, if you've got a series made up of these kind of terms, they're positive terms and they're always smaller than or no larger than b sub n, then let's look at these series. Sum from n equals, 1 or whatever finite number you want, n to infinity of a sub n and b sub n. These series have to inherit that inequality. If this is always less than or equal to this, then the sum, the infinite sum, has to be less than or equal to this. Now this is good for one of two things. It depends on what you're trying to prove. So suppose that you know that b sub n converges to something so that this series converges. It's finite. If this is finite, what does it say about a sub n? It also has to be finite, right? There's no way that this could be infinite if it's less than something which is finite. So one possibility is if this series converges, b sub n converges, then so does a sub n. So that's one possibility. Well, let's take a look at another possibility. What if a sub n diverges? That is, what if this sums up to some infinite total? So the second possibility is if this sum a sub n diverges. Its sum is infinite. What does that say about b sub n? What has to be true? It diverges. So if this is summing up to infinity and this is smaller than this also has to diverge. So if a sub n diverges, then this series diverges. So it just kind of depends on what you're trying to prove, and it helps to have a good idea of what you're trying to prove. So what you're going to do is you're going to look at your series and go, well, it's close to this, and that converges, or it's close to this, and that diverges. So it's helpful to know roughly what to expect, even without necessarily doing the complete proof. So let's start with a few examples. Starting with problem number 4. sum from n equals 1 to infinity of 1 over 3n squared plus 2. Now this one, let's see. Let's think about it this way. Now you can't do this in terms of a proof, but at least it gives us an idea of what to expect, roughly speaking. This, other than the plus 2, kind of looks like this. N equals 1 to infinity of 1 over 3n squared. And the 1 over 3 part, that 1 over 3 can be factored out. So I get n equals 1 to infinity of 1 over n squared. So I'm looking at something like this. Now what could you tell me about this series? That's a p-series, right? And what do we know about this particular p-series? Yeah, p is greater than 1, so it converges. All right, so we're kind of thinking that this might converge. Is this a p-series? No, it's not. End of story. It's just not. So, nor does it look like it's something that you could easily do by integration. It's not a geometric series. It's not a telescoping series. You kind of need something else. So, we've got the direct comparison test. And fortunately for you, this one's set up in a nice direction. 1 over 3n squared plus 2. If I make my denominator smaller, I make the quotient bigger. So this is going to be less than 1 over 3n squared. Perfect. Now, this is my convergent p-series. Yes? If you make the denominator smaller, then you're going to make the overall quotient bigger. So for instance, let's look at it with some numbers. If I have 1 over 10 and 1 over 8. If I make the denominator smaller, I make the quotient bigger. So 1/10 is smaller than 1/8, or 1/8 is bigger than 1/10. So what we're doing here is we're removing that and saying, all right, this series is going to be less than this one. This one I know is a convergent p-series. So this series converges by the direct comparison test. You have to pardon me, but I'm not going to write that out. Converges by the direct comparison test with the convergent p-series bless you, of sum from n equals 1 to infinity of 1 over 3n squared. And then 1/3 comes out, so it is just a multiple of a p-series. Maybe I shouldn't call it a p-series. Maybe just convergent series would be a little bit better here. But it's clear that this series converges because you can take the 1/3 out and it becomes a convergent p-series. Nice. So it's a quick way for some problems to get a convergence or divergence. So you just have to be careful with the inequalities. That's all you have to do. Okay. Comments or thoughts on problem number 4 here? Yes. Yeah, you're going to have to kind of in your mind decide if you think it converges or diverges, and then pick a series that helps you finish off your proof. So if I had something that diverged, I'd want to pick a divergent series that's smaller than that. So that, okay, this diverges so that this one diverges. If I have a series that I think is going to converge, then I want to pick something like I did here. I want to pick something bigger than that. So it kind of depends. You got to be a little bit careful with the direct comparison test.
So you kind of have to think ahead.
Yes. Yes, you have to think ahead. Yeah, you don't want to just pick one at random. Now, some of these series become a little bit tricky. In fact, what was nice about this one is that I had a plus in the denominator. So I could just say, oh, well, let's get rid of the 2. And then I had this, which is this. I knew that one converged. If this was a minus, then I'd be in trouble. Let's take a quick look at what would happen if I did the minus. If I had a sum from n equals 1 to infinity of 1 over 3n squared minus 2, well, you know, I still expect that this thing is going to converge. It's just that I don't have a nice convenient thing to compare it with anymore. Because if I was to look at 1 over 3n squared, then unfortunately the inequality is going to run this way. This is a smaller number. This is a bigger number. So the bigger number in the denominator means it's a smaller fraction. So this doesn't help me. I mean, it's nice that this is true, but let's take a look at what's going on here. Let's see. I've got the sum from n equals 1 to infinity of this, 1 over 3n squared, is going to be less than the sum of n equals 1 to infinity of 1 over 3n squared minus 2. If this is finite, does that tell me anything about this? Could this be finite? Could this be infinite? Could be either one, right? So the inequality doesn't run in the proper direction. It doesn't tell me anything. You have to do this in the right direction. So it's one of two things, like we said earlier. If this one converges, then so does this one. If you have something that diverges, then if you want to prove divergence, if this one diverges, then so does this one. But you have to be careful about the order. So it's for this reason that I sometimes recommend, actually I often recommend just people use the limit comparison test. We'll do a couple more of these and then we'll do the limit comparison test. Anything else on problem number 4? It's a great question. I hope you see that this one doesn't work. You know, if I had a minus here and I said, oh, I'll just get rid of the 2, this being finite doesn't tell me anything about this. This could be finite or it could be infinite. You just don't know. Yeah.
So basically you're saying, like, sure, that might be true, but it's not going to help.
Yeah, but it doesn't, knowing something about this doesn't tell me anything about this. It could be finite, could be infinite, don't know. I think it'd be finite. We'd have to still prove it, though. And nothing that we have right now would prove that. I mean, I think maybe you could do some kind of a brute force integration, maybe. It would be really, really awful. All right, so let's try some more here. Let's try problem like number 6. The sum from n equals 1 to infinity of 4 to the n over 5 to the n plus 3. So similar kind of thing here as with the last one. What does this kind of look like if we kind of monkeyed with it a little bit? Let's just kind of innocently do one of those. Put your fingers on the scale, right? So wouldn't it be nice if we could get rid of that thing? What would we be left with? 4/5 to the nth power. Basically a geometric series. So let's kind of wink and nod and go, you know, boy, it'd be really great if we had 4/5 to the nth power. Why would that be great? What would that be telling us? It's a geometric series. Not only that, but it's a convergent geometric series, right? Because the ratio here is less than 1. So, wow. There's more good news. 4 to the n over 5 to the n plus 3 is less than 4/5 to the nth power. perfect. So, because these are both positive valued terms and this inequality, because this converges, in fact, we can calculate what it converges to, and this series has to be greater than this series converges by the direct comparison test with this one. So this series, 4 to the n, 5 to the n plus 3, converges by the direct comparison test with this. And I know this converges because it's a convergent geometric series. So it's nice. It's a nice, easy way around showing some convergence for some problems. You just have to be careful with the order that you work things. Let's see. Let's try problem number let's try problem number 10. The sum from n equals 1 to infinity of 1 over 4 times the cube root of n minus 1. Now let me just double check. I do not believe that 1 is underneath the radical. It's not. So let's see if we can't figure out what we think is going to happen with this one. Do you think it's going to converge or diverge? What would you kind of guess? What series might you want to look at as you think about whether or not this one's going to converge or diverge? Yeah, a p series. So actually, not a 4 up there. 1 over the 4th root of n, 4 times the cube root of n, which is 1/4 n equals 1 to infinity of 1 over n to the 1/3 power. So is this going to converge or diverge? What do you think? Yeah. Well, wait. Converge or diverge? Diverge. This is a divergent p series. So that's going to diverge. Okay. Well, here's a good question for you. 1 over 4 times the cube root of n minus 1 and 1 over 4 times the cube root of n. Which way does this inequality run? Is it a less than or a greater than? Which one? Greater than. And that's perfect. That's what we need. It's exactly what we need. Because that tells us that this series is less than this. So the sum from n equals 1 to infinity of 1 over 4 times the cube root of n is going to be less than the sum from n equals 1 to infinity of 1 over 4 times the cube root of n minus 1. Actually, we should probably start the series at 2. Can anyone see why? No, actually, you know what? We can get away with 1. Yeah, could have gotten away with 1. It doesn't really matter. Finite number of terms is not going to affect the convergence or divergence of a series. But we know that this one diverges. It's a divergent p-series. If this sums up to infinity, could this be finite? If this is summing up to something infinite, could this sum up to something finite? No, it can't. If this is infinity, this has to be infinity. Just no choice. So, therefore, this series diverges by the direct comparison test with this one. 1 over 4 times the cube root of n minus 1 diverges by the direct comparison test with this series. Nice. Okay. How are we looking for number 10 here? Okay. Quick brief aside here. So the other day I had some root beer. Or another way to express that is this, right? All right. Question, what's this? It's square glass. So what did I do? I poured my root beer into a square glass, and I got beer. All right. All right. Don't forget to tip your servers. I'll be here all week. Okay. Let's keep going. You want more of those? All right. Let's see here. Slideshow from current slide. All right. I was going to do this one later, but you guys seem like you need a little bit of something now, so here you go. Let's see. We already did that one, so here we go. So, what do you get if you measure the circumference of your pumpkin and divide it by its diameter? What do you get? Pumpkin pie. Ah, come on, that's seasonal, man. You gotta give it up. Give it up. All right. All right. All right. So that's all I got right now. Catch me later. All right. One last one. Why do mathematicians like going to the national parks? There's lots of natural logs. Dude. All right. Let's see. Let's take a look at problem number 12 real quick. Now, keep in mind that on an exam, I'm not going to tell you you have to solve it. You still likes that one. I'm not going to tell you have to do it this way or you have to do it that way. It's going to be completely up to you as to how you want to solve these things. So in particular, problem number 12, you've got n equals 1 to infinity of 3 to the n over 2 to the n minus 1. What would be your guess? Is that looking like a convergent series or a divergent series? If you're looking at this and, kind of thinking, that's close to this term, 3 over 2 to the n, diverges, right? Why? It's bigger than 1, yeah. So it's looking like it would diverge. You could run through the direct comparison test and do it that way. But keep in mind, there's more than one way to, quote-unquote, skin a cat, right? In this case, this fails the nth term test. These terms, as you go out towards infinity, don't get closer and closer to 0. They get closer and closer to infinity, actually. So the limit as n approaches infinity of 3 to the n over 2 to the n minus 1 does not equal 0. That's it. So that's a quick way to decide convergence, or actually in this case divergence of a series. You could use the direct comparison test. Problem with the direct comparison test that people run into is they get it backwards. They have the inequalities running the wrong way, like this one. Sure, this is finite, but that doesn't tell you if this is finite or infinite. So, wow, that doesn't help you. Yes?
Do you have a tip or something to make sure you don't do it backwards? How to try to
Yes, my tip to make sure you don't do it backwards is not to use the direct comparison test. Is to use the limit comparison test. So let's talk about. I seriously, that's probably the best way to do it, is to use the limit comparison test. So the limit comparison test is going to be very similar to the direct comparison test. Maybe a touch more work, but it's safer. So if I was going to recommend something that would be safe, it's the limit comparison test, because you're still going to be using the series that you kind of want and think this compares to, but you're not going to have to think hard about the direction of the inequalities. So that's why I like the limit comparison test. And let's take a look at that. Let me flip over to page 614. So, again, you have two positive valued series. So this is not something that's, up and down, left, alternating or anything like that. They're strictly positive values. If the limit of one divided by the other is finite and positive, basically, let's write it like this. 0 is less than L is less than infinity. All it has to be is positive, it cannot be 0, and it has to be less than infinity. If that's positive, then either both of these series converge or they both diverge. So they behave the same. You don't have to necessarily fuss around so much with, oh, gee, one of them is less than or one of them is greater than the other one. So let's apply that. Right sound? Yes. Okay, we're good. All right, good thing I noticed that then. 2 to the n plus 1 over 5 to the n plus 1. This would be a real bear to try and deal with if you're doing the direct comparison test. But with the limit comparison test, shouldn't be too bad. So find a series that you think looks like this and will behave like this. And try and do the limit comparison test. Mimi and I will walk around and taunt you. Help you. steps. Just a token one or two, just to keep your instructor happy. Okay, so the series of choice for this one, at least as far as my money is concerned, is just this one right here, right? 2 to the n over 5 to the n. The nice thing about that one is that it's a convergent geometric series. N equals 1 to infinity of 2 to the n over 5 to the n. So if our limit converges, then this one will converge by the limit comparison test. So a sub n here, b sub n here. The limit as n approaches infinity of a sub n over b sub n, 2 to the n plus 1 over 5 to the n plus 1 divided by 2 to the n over 5 to the n. Oops. So it looks like I have a plus 1 here. Realistically, it's just a little dust on the lens. There we go. Perfect. Thank you. All right. Let's invert and multiply. So that's going to be the limit as n approaches infinity. When you invert and multiply, let's see what we're going to get. I'll have 2 to the n times 5 to the n. That'll be 10 to the n plus 5 to the n over multiply again. So that'll be 10 to the n plus 2 to the n. Let's pull that trick that we did with our polynomial term just a minute ago. If I multiply everything here by the largest term in the denominator, or divide everything in this by the largest term in the denominator, so 1 over 10 to the n, 1 over 10 to the n, then I'll get something that simplifies like this. N approaches infinity of 1 plus 1 over 2 to the n over 1 plus 1 over 5 to the n. And now we can just pretty much plug in the limit. You get 1 plus 0 over 1 plus 0 is 1. Yeah, you get the cancellation. So now the nice thing is again, this is finite. You don't always have to engineer this to be 1. That's just the way they've been coming out. That's typically what happens when I work on these things. But if this came out to be 11, 1100, or 1,000,000, or whatever it is, as long as it's finite, between 1 and 0, or between infinity and 0, then by the limit comparison test, we're okay here on problem number 16. So therefore, by the LCT, with this series, n equals 1 to infinity, 2/5 to the n, this series converges.
When you times that, wouldn't it be 10 n squared? When you times that.
Oh, this is 1 over that.
Go to the left. When you invert that 2n on the top, doesn't that? I mean.
So that'd be. So what's going to happen is you're going to have 5 to the n times 2 to the n, which is the same thing as 5 times 2 to the n, or 10 to the n.
Oh, okay. I thought it was squared.
No, it's a good question, and I appreciate the question. So by the limit comparison test, this one converges. 2n plus 1 over 5 to the n plus 1 converges. Well, thanks for the question. Let's do a little bit of review here. We now have a total of, I think, 7 tests. You've got the P-series test, the integral test, geometric series test, telescoping series, nth term test, direct comparison test, and the limit comparison test. Thank you, squared. Okay. What I like to do is give you a series of problems and not ask you to really go through all the steps, but just think about, well, what would you do? Which one of these tests would you use? So for that, let's take a look at problems 24 through 30. Let me write them down here for us. Now, there's really more than one answer for a lot of these. So we'll definitely, when I grade papers, I'll accept more than one answer. Just depends on the problem. Problem number 24 gives us this series. Sum from n equals 0 to infinity of 5 and negative 4 over 3 to the n. So there's two things that I'm going to want from you. And this is just like my 2-minute drill that you'll see on the exams. So when you take your exam and it comes to this part, give yourself 2 minutes to work this problem. All right, I'm kidding. I just call it the 2-minute drill. So problem number 26. Now the book has a typo here. N equals 2 to infinity of 1 over n cubed minus 8. Why is that a typo? What happens at the first term? Yeah, you're dividing by 0, right? 2 cubed minus 8, 0. So let's do 3 to infinity. Problem 28. Sum from n equals 1 to infinity of 1 over n plus 1 minus 1 over n plus 2. And last but not least, problem number 30. Sum from n equals 1 to infinity of 3 over n times n plus 3. So make a friend, give yourself a couple minutes, look through and decide, all right, well, what test would I use? And do I think it's going to converge or diverge? Make a prediction. Now, when I grade these on an exam, this is how I weight it. That's 3 points. That's the important part. This is 1 point. Look, you can guess there. Believe it or not, sometimes people leave that blank. I don't know why. All right? You've got a 50-50 chance. I'm not penalizing you for guessing, so take it. All right. But go through these things. Your choices, once again, are the nth term test, the P-series test, the integral test, the limit comparison test, geometric series, telescoping series, and direct comparison test. So try and get at least one test for each of these. Some of them are going to have more. Buddy up, partner up, make a friend. You got the videos to look back on. They'll be there. I hope they're helpful. Okay. Let's take a look here. What tests can you use here? Geometric. Did anyone think of anything else that you could use here? Nothing? Got nothing? So I should only accept one answer on the exam? No? What about the nth term? Right? I mean, the limit of these things doesn't go to 0. So, yeah. Nth term test. So that's an easy one that you can pick up. What do you think? Is it going to converge or diverge? Diverge. It's a big diverge. This one's not going to 0. Diverge. You better not use this with converge. I'll take off extra points. I'll take off 6 points on a 4-point problem. Donnie. What? Because 4 over 3, this is a geometric series with r, that ratio is bigger than 1. If you take a look at the absolute value, it's bigger than 1. The negative sign doesn't really change much for this particular problem. You can get convergent series that have, negative values of r. If this was a 2/3 instead of a 4/3, it would converge. All right? Good. How about the one below that? Is that a p-series below that? It's close to a p-series, but it's not a p-series. A p-series would have to be something like this. I couldn't have that -8 there. So it's not a p-series. Sorry. Minus. Sorry. All right. Limit comparison or the direct comparison test. So LCT or DCT with what series? Yeah, 1 over n cubed. Now, on the exams, if you're going to choose to do a limit comparison or direct comparison test, I'm going to ask you for the series that it goes with. Yes, ma'am. Great question. Why can't it be the nth term? Nth term is only for showing divergence. So, what do you think? Is this one going to converge or diverge? Converged, right? Because it's a p-series. So this one converges. So, yeah, that's what you got going on that one. It converges. The nth term test can only go with diverges. Do not put the nth term test down here. All right, but I appreciate it. Yeah, go ahead. Well, because when you look at this, you look at that and say, oh, well, that's kind of like this. Now, this is a p-series, right? And what do you know about this p-series? Since that's greater than 1, what's the series going to do? Converge or diverge? Converge. And if it converges, then I shouldn't be using the nth term test to show convergence. Nth term test cannot show convergence. It's some of you are going to see it when you get back to your exam in a couple weeks. And I'll write out nth term test cannot show convergence. And by the end of the night when I'm done grading, I'll be gritting my teeth. Like, nth term test cannot, because I'll be writing it again and again and again. I should come up with some acronym for that. Yeah, a stamp for it. There we go. Boom. Then I can get my aggression out at the same time, right? Boom. All right. I know it's tempting. I've taught this course a lot, and Yeah, that nth term test. It's convenient because you get a quick, easy. Oh, it diverges, but yeah, you can only use it to show divergence. All right, how about this next one? That one's pretty straightforward. Out. Telescoping series. Good. Telescoping series. Converge or diverge? Mumbled under the breath. Yeah, all right. Converges. That one's going to converge. How about the last one here? What would you do there? You probably could, if you did a partial fraction decomposition, you probably could do this as a telescoping series. I guess it would depend on the partial fraction decomposition of this one, but it could be a telescoping series. So telescope maybe. What else? Yeah, I'd say the LCT or DCT. Well, let's see, DCT. Let's see. I'm not sure if the DCT would work. Actually, I should probably be a little more careful. One of these is going to work, and one of them won't. Let's see, DCT. +3. Yeah, the direct comparison test will work here. Direct comparison test won't work here because if you get rid of the 8, then that would be bigger than this term. And the direct comparison test actually wouldn't work here. So, yeah, you have to think about that one a little bit. And it's a good idea that maybe you just stick with the limit comparison test. Limit comparison test, you don't have to be as careful with the direction that the inequality works. And this one, we'll take a look at it. It's the dominant term in the denominator is going to be an n squared term. So it's going to converge. All right. At the start of this or sometime this evening, I promised a little pecking order here, and it's this. It's how fast these terms grow. And it's just a good thing to keep in mind. You know, what terms grow the fastest, what terms grow the slowest. In terms of slow-growing terms, some of the slowest growing terms you're going to get are going to be your ln of n terms. Those are really slow-growing functions. So we can see that here. So I've graphed the natural log. Something that grows a little bit faster than that is your square root function, although not much. It's still a very slow-growing term, but it is going to be bigger in general than your natural log term. So we've got a little pecking order like this. The next thing there after that is going to be your polynomial terms. So your polynomial terms, let's just throw in like an x cubed function, and you can see a dramatic difference in this. So x cubed, that takes off pretty quickly and grows really, really fast. So that's going to be your polynomial terms, n to a p power. And then the next term after that, what's going to come next? Exponential terms. So let's shut this one off and compare that to the growth of an exponential function. Now, it looks like the cubic function is bigger for a little while, but eventually the exponential term is going to really, really take off. When I teach intermediate algebra, what I like to do is I'll scale the x-axis in terms of centimeters. And by the time you get out to 20 centimeters, in order to graph a simple function like 2 to the x, to graph 2 to the 20th power, you'd have to be about 6.5 miles high. To graph 2 to the 34th power, you'd have to land on the moon. And by the time you get to 2 to the 60th power, you'd have to go to Proxima Centauri, which is the nearest star, about 4.26 light years away. In other words, it's a really, really, really fast-growing function. And it's not the fastest one in our arsenal. So let's take a look back here. The next one is going to be, a to the n power. So that's going to be your exponential functions. And then after that is your factorial functions. So your factorial functions grow even faster than these already fast-growing functions. So, wow, can't imagine that. I mean, so it's going to be n factorial. And there's one that's even bigger than that. And that's n to the nth power. And that's the one that I was kind of fussing with earlier, trying to figure out, well, gee, what value of n is going to be bigger than, like 2 to the 20th? But that one just grows unbelievably fast. So that's even faster than a factorial by a wide margin. Cool. So it's helpful to keep in order, keep this pecking order in mind, because you're going to have to decide, well, which one's growing faster. And it just helps you decide if you think one's going to converge quicker than the other. Let me give you some homework. For homework, try 3 through 29 and 33 through 41. That's section 9.4. Cool. All right, let's take a break.